not do anything more about that. But what I do during the lectures or the labs is I usually read what I write or I write what I say. So kindly pay a little bit more of attention when I am writing or speaking. Or if you don't, if you cannot read anything I write, just let me know in the chat, or you can raise your hand and then I'll recognize you so that I can clarify things out. Right. So now computing volumes. There are two types of volume problems that you discussed in the lecture. The first one would be computing volumes of solids with known cross sections and bases. And then the other one would be solids of revolution. But perhaps I'll start with some examples about solids with known cross sections and bases. So the idea here is you will be given two information, or at least two information about the solid that you want to compute the volume of. You will be given how the cross section looks like, or sorry, first how the base looks like. So I suggest you draw at least a rough picture of how the base look like. So perhaps say you might be told that, okay, this would be the base of my solid, right? So let's highlight this. This is the base, the region R. Of course, this will be given by some function y equals f of x. Usually you have the x-axis, or sometimes you have, say, y equals g of x over there, okay? And then aside from the basis or the base of the solid, you will be told how the cross sections look like, right? So the idea here is that the cross sections could either be perpendicular to the x-axis or perpendicular to the y-axis. Well, if the cross sections are perpendicular, so I'm going to use this notation for perpendicular. So take note for the rest of the class, when I write something like this, that means perpendicular, right? So if the cross sections are perpendicular to the x-axis, then you will use dx, okay? On the other hand, if the cross sections are perpendicular to the y-axis, then the variable of integration would be y. That will always be the case, okay? And then say here, I know that for this particular example or illustration, say the cross sections are perpendicular to the x-axis. So that means you will have vertical strips over here. So the volume will be given by an integral with respect to x, because I assume here that the cross sections are perpendicular to the x-axis. So I need the bounds for x. Say the region started at x equals a and ended up with x equals b. So the bounds will be a until b. Then what's the integrand? Well, since we are dealing with volume, the integrand will not simply be the height of the vertical strip, but would be what? This would be the area of the cross section. And this area will be given in terms of the variable x. So it is important to take note how the cross section looks like, right? Usually you will be given special objects or special shapes for the cross sections. I guess for Cal 1, the usual choices would be squares, semicircles, or perhaps the hardest would be equilateral triangles. But say you have squares as your cross section, so you can imagine having having squares that are sticking out of my screen. So basically, and I will ask for your imagination here because I'm not good at drawing three-dimensional objects. So basically say if the cross sections are squares that are perpendicular to the x-axis, so you will have squares that are sticking out of the page over here. So on top of this region R, you will have infinitely many squares sticking out of your screens as your cross sections. And I hope you can imagine how the solid will look like. So if you have a cross section, if you have a vertical strip here, there is a corresponding square that will stick out of the page. So basically, you can imagine the solid to be infinitely many thin squares that are stacked very close to each other, thus producing a solid. Okay, can you guys imagine that? I will rely much on your imagination over here because I'm not good at drawing those objects. But I hope you get the picture. Is that good? All
I
right.
imagine like a blob of jello. I don't know why.
Yeah, exactly. Something like that. So you have your plate as your base, and then on top of that plate, you will have jellos that are squares in shape, right? And then the idea is, how do we get the volume of that solid? Well, you can imagine that solid to be formed by infinitely many squares that are stacked together. So basically, the volume or the amount of material, as they say in physics, that is needed to construct your solid will just be the summation of the areas of those squares that served as the building blocks of the solid, right? But the problem there is there are infinitely many squares, and they are closely packed to each other just to create the volume. So a summation of the areas of those squares will not be enough because they are squares that are very, very thin that are placed next to each other. So that's why instead of a summation, we do integrals. Remember, integrals are the infinite and continuous versions of summations. So that's why the formula for the volume of such solids are represented by the integral of the areas of the cross sections. In layman's terms, this is the continuous summation of the area of those cross sections. And the idea is that the amount of material needed to create that solid is just the summation of the areas of those cross sections that we stacked next to each other. There are infinitely many of them. That's why we use integrals. And I hope that clarifies or that gives some sense into why we have this formula in front of you. That's the thing, because usually formulas are easier to remember if you know the reasoning behind them. So basically, integrals are continuous summations. So the volume is just a continuous summations of the cross sections, right? Because of that idea of how this solid would be formed. Okay. And with that intuitive notion, let's try to look at some specific examples. So let me scroll up and copy paste problem number 10. I hope that made a little bit more sense than just looking at how the formula looks like and just memorizing it for the sake of computing things. I usually want to go behind the formula, why is it so that it's easier to remember. Okay, let's do problem 10. So here, the base of a solid is the region bounded by the circle x squared plus y squared equals 9. So basically, I'll draw a picture here quickly. Okay. Remember, x squared plus y squared equals 9 is a circle centered at the origin of radius 3, right? If you remember your conic sections. So I'll have a negative 3 here, negative 3 here, and 3 here. Then I'll have a circle. Imagine that's a perfect circle. And then this is the base of our solid, the base of our solid. And then what's next? We were told that the cross sections are perpendicular to the x-axis. So that tells me, okay, the volume will be an integral with respect to x. Because again, the cross sections are perpendicular to the x-axis. Now, knowing that I am integrating with respect to x, I need the bounds for x. Of course, you could use some symmetry over here, but I'll forget about that for a moment. Let me do the entire integration without assuming any symmetry. If I look at the shaded region, it started when x is equal to negative 3, and it ended up when x is equal to 3. So the bounds for the integral would be from minus 3 until 3. And then the cross sections are squares. So here I will have a vertical strip because I'm integrating with respect to x, and that vertical strip will correspond to a square that sticks out of the screen. Okay, so basically that's how the cross sections look like. So they are squares that are sticking out of the screen that is drawn on top of this circle. So I hope again you can use your imagination to picture this out. Now, if we follow this idea, the solid is formed by superimposing or stacking together infinitely many squares lying on top of the circle, right? So if I have a vertical strip here, that corresponds to another square. I do that infinitely many number of times, I'll get my solid, right? And that tells me to get the volume, I just need to sum up the areas of those infinitely many squares. But what is the area of these squares? Well, remember the area of a square is side length squared. But what is the length of a side here? Well, the length of a side will just be how long is this guy, right? Maybe I should erase the other, okay, the other square. So basically what we do is, okay, the side length S would be this length over here. How long is this strip? But remember, this is exactly the vertical strip that we drew. And remember from last time, to compute the height of a vertical strip, that would be the top function minus the bottom function, right? But what are these functions? Remember, we are dealing with a circle of equation x squared plus y squared equals 9. And then I solve for y in terms of x. I'll get y squared equals 9 minus x squared. And then y is equal to plus or minus root of 9 minus x squared. Good. Now, why do I have two options here? Remember this top portion? That is the one that has an equation y equals root of 9 minus x squared. And the bottom half of the circle, this guy, that has equation y equals negative root of 9 minus x squared. Okay, so that means S. Okay, so S, the side length would be top function minus the bottom function. So that will be root of 9 minus x squared minus negative root of 9 minus x squared. So that will be twice of root 9 minus x squared. All right. And then remember the integrand would be the area of the square, which is s squared. We already know that s is equal to this. So the integrand over here would be 2 times root of 9 minus x squared quantity squared. All right. Or if you will use symmetry, which is perfectly fine because we know that the circle is symmetric with respect to the y-axis, well, what you could have done is to integrate instead from negative 3 to 3, just integrate from 0 to 3, same integrand, but multiply it by 2. Right? Because the volume will be the volume of the right hemisphere times 2, or the right semicircle times 2. Right? And since if you look back at the problem, it asks for the actual volume. So you need to evaluate the integral, which is which is easy because remember, you still have something squared. So the square roots will be gone. If you carry out the calculations, I guess the answer would be, I calculated it beforehand. The answer is 144 cubic units. Okay.
Excuse me.
All right. Yeah. Go
Can
ahead.
you explain one more time why you changed the boundaries?
Okay. For the second integral?
Yes.
Well, the only reason why I do this is perhaps you might want to use symmetry, because remember that the base of your solid is all over the entire circle, right? From -3 to 3. Probably you notice that, oh, the circle is symmetric with respect to the y-axis. So I can just integrate from 0 to 3 over here, this shaded region, right? And then compute the volume, which is this guy, but multiply the result by 2 because I have another half here that I didn't include in the integration. So yeah, so you can use this. I only did this if I want to take advantage of the symmetry. Of the symmetry of the circle. But it's perfectly fine if you don't want to take advantage of the symmetry. You could have just left your answer this way and then just forget about this. If you don't want to take advantage of the geometric symmetry of the shaded region, which is perfectly fine. Anyway, you'll get the same answers once you compute those integrals. So maybe that could cause some confusion. So maybe I'll just cut this out. Okay, is that fine? So it's up to you if you want to use symmetry or not. But rest assured that if you had the right setup and you evaluated the integrals correctly, then you should get the same answer.
Okay, thank you.
All right, any other questions? Okay, none. Let me try problem 12. Hold on, let me scroll up. Okay. I'll skip problem 11. I'll leave that to you guys, but I'll include the solution to that in the next update for the worksheet. Well, it's the problem 10 and actually problem 11, because here the cross sections are again squares perpendicular to the x-axis. So your solution would be similar to problem number 10. The main difference with problem number 10 is that the solid is bounded by a parabola, or the base is bounded by a parabola, but that is similar to what we have in problem 12. So you can pick up the bits and pieces of our solutions from problems 10 and 12 and then to come up with your own solution to problem 11. So try problem 11 on your own, compare your answer with the one that I will upload later today. So yeah, that will be a good practice. Okay, let's do problem 12. Okay. Okay, so what do we need to find for problem 12? Problem 12 simply asks for an integral that gives the volume. So we don't need to calculate the volume. So once you have the integral, do not evaluate it unless you are specifically told to do so to save time for, say, exams or quizzes. So I take note for problem 12, I only need the integral. No need to evaluate, right? Now, what is the base here? The base is the region bounded by this curve. Faiza is asking a question. Will the problem always indicate what shape the cross sections are? Yes. The problem should tell you what the cross sections or how the cross sections look like. It should give you the position relative to the x or the y axis, and it should also tell you the shape. Usually for Cal 2, we only deal with squares, semicircles, and I guess sometimes equilateral triangles. So yeah, those are usually the three basic shapes that you need to remember. Okay, going back to the problem, the base is on the first quadrant, bounded by the parabola 9 minus x squared. 9 minus x squared is a parabola opening downwards with vertex when x is equal to 0, giving us y equals 9. Okay, there we go. And then the point of intersection here, when y is 0, x is equal to 3. Okay. Maybe I'll put the 3 over here. This is x equals 0. This is the region R. Okay. And then we were told next that the cross sections are perpendicular to the x-axis. So that means I know that the volume would be in terms of the variable x because the cross sections are perpendicular to the x-axis, right? So my bounds would be bounds for x from the figure. I already figure out that the region will start at x equals 0 and will end when x is equal to 3. And then what's left to be determined is the integrand. But the integrand, remember, is the area of the cross sections. The cross sections were said to be semicircles. So we need the formula for the area of a semicircle. But that is nothing more but half the area of a circle. Circle has area pi r squared. We are dealing with semicircles here, so it's just 1/2 pi r squared. And how does those cross sections look like? So they will look like this. Semicircles sticking out of the screen. So that's how our cross sections look like. Okay. And then now, how do we find the area? Well, if we look at this rough sketch here, the length of the strip tells us the diameter of the semicircle, right? And the diameter is basically the height of our vertical strip. Now the vertical strip, again, this is top minus bottom, right? The top function corresponds to the parabola 9 minus x squared, minus the bottom function is the graph of the bottom function is the x-axis, which is the line y equals 0. So that's why I have a minus 0 here. So that's 9 minus x squared. But be careful here, that's the diameter. So the radius would be half of that. So that's going to be 9 minus x squared all over 2. So that's the formula for the radii of the cross sections. Okay. Then I'll just simply plug that into the formula for the area of a semicircle. So it's going to be 1/2 pi times the radius. So that's 9 minus x squared all over 2 quantity squared. Then let me simplify a bit. This would be pi over 8 times 9 minus x squared quantity squared. So that's the area of the semicircle. So I'll just use that as my integrand here because we get the solid by superimposing or by stacking together infinitely many semicircles with area pi over 8 times 9 minus x squared quantity squared. Basically, I'll have this. And since the problem is just asking for the integral, I don't need to evaluate it. So that's going to be my final answer. And I won't spend time evaluating this integral because the problem is not asking for it. All right. Any questions? Any violent reactions? You guys are very quiet.
Can you explain that how you got the area again, like the pi over 8?
Okay, so let's see. So I got this first step by just taking half of the area of a circle because we are dealing with semicircles. And then is it clear how I got this? This is the radius, right? Coming from our analysis over here. Okay. And then I got the pi over 8 by doing algebraic manipulation because here I have 2 in the denominator, but that should be squared. So I'll have eventually a 4 in the denominator. And then there's a 2 outside. That's why I got the 8 over there. Pi is copied over. And then 9 minus x squared quantity squared is just the numerator over there. Okay. Now, if you want, you could have just copied this entire thing into the volume, into the integral, and that's perfectly fine with me, right? Even if you didn't do the algebraic manipulation to pi over 8 times 9 minus x squared quantity squared. And I hope you guys see the utility of sketching at least a rough picture of the problem. So you can from there analyze how the figure looks like, how the strips are related to the area of the cross section. So it would be easier to compute what's the length, what would be the diameter, and so on. Okay. Any other questions? You're probably still hang over the weekend, so any other questions? If none, then I have a question for you guys. So there's still one more problem for cross sections involving or for volumes involving cross sections. Problem number 13. Do you want to go over it, or let's go to solids of revolution?
Wait, what?
Yeah, I have one more problem about cross sections in the worksheet, a very similar one to problem 12. Do you want to go over it, or should we skip that and then let's go ahead to the next topic, which is about solids of revolution?
I don't know what the second one is, so.
But there are no other questions about cross sections, or cross sections kind of easy for you? Do you get the general idea?
So, I mean, the only question I have is the only reason you didn't expand that polynomial is because you weren't asked to evaluate it? Or would you expand that if you were? Like, would you leave it like that if you were asked to evaluate that?
If you were asked to evaluate this, then you need to expand it, because you cannot do a u substitution for this integral. So you will be left no choice but to expand the 9 minus x squared quantity squared into a trinomial and do the integration term by term.
Okay.
So that's why it's important to take note what the problem is asking for. If it's just asking for the integral, then you don't need to calculate anything. You don't need to expand anything, as long as you can set up the integral and the integrand properly, then no need to show off your algebra skills. But if the problem is asking for the actual volume, then you need to expand everything, simplify everything, compute for the integral. Okay? So, okay, no other questions? You're exceptionally quiet today, but okay. I hope that's fine, because most students find this easy. The only challenge here is actually determining the formula for the cross section, for the area of the cross section, which I guess you can find by having a rough sketch of the region, identify what its parts and how the strips are related to the parameters of your shape, be it the side length, be it the radius, and so on. Okay. Now I'll go ahead to solids of revolution. My problem